So let's start with my collaborators. So this is a project that I started doing in the Illinois Geometry Lab together with Professor George Francis. And we worked with several undergraduate students that you can see on the slides, working with different kinds of frameworks. And the reason we started working on this project was because of Tony Robin. Tony is a mathematical artist, and he is interested in visualizing higher dimensional objects in 2D or 3D. And here you have a painting by Tony. And some of the objects that are shadows of higher dimensional objects are quasicrystals. Okay, and Tony is interested in studying quasicrystal frameworks. So I'll just start with a picture of this structure. So this is a quasicrystal framework. So when you think of a 3D quasicrystal like the one you see on this picture, you should think of rhombohedra. There's a fat rhombohedra and a skinny rhombohedra, and these are tiling the three-dimensional space in such a way that there's no symmetry. This is not a periodic tiling of the 3D plane. And these frameworks are very beautiful to look at. The problem that Tony was considering is that he wanted to build these sculptures like the one you see here, and he wanted to make them rigid so that it can hang like the one you see here. But the way he was thinking about it is that he would plate some of the faces in this framework, and when he was plating these faces of the framework, he noticed that, you know, the place where he puts these plates really helps for the rigidity of the structure. So the question he asked George Francis was, where should I put the plates in this quasicrystal structure in such a way that the structure is rigid? And the reason Tony is interested in these structures is also a reason, you know, these are very beautiful, but also when you have these plates on the structure and you have lighting on top of the structure, you can see a shadow on the floor of the picture. And when this light changes around, you would see different patterns in on the floor. So this is a very nice structure, and plating them with these translucent colored plates makes for a beautiful mathematical structure. So this is the problem that we're considering. How can we make these rigid with plates? And there are other structures you can make, like this quasicrystal composition made of rhombi. And we wanted to help Tony with his question. So we thought, okay, let's first start understanding the same problem in 2 dimensions. By the way, if anybody has a question, just feel free to interrupt and you know, ask any question that you have. I'm happy to explain more or tell more stories. Okay, so we started looking at the 2D case. So here we're considering quasicrystals in 2 dimensions. So what this means is we're considering Penrose frameworks, and these are tilings of the plane by 2 types of rhombi, a fat and a skinny one, in such a way that there is not this is not a periodic tiling of the plane. So the question we are starting with is, you know, how can we make a Penrose framework rigid? And let's quickly go over some basics of frameworks. So I'm considering bar and joint frameworks. So what this is this is a graph G and an embedding P of the vertices of G in two space or three space. And the vertices of the graph are the joints, and the edges of the graph are the bars. And in many cases, these bars will have the same length, but not necessarily. And I am interested in these types of frameworks. Okay, and we know that in 2 dimensions, there are the Laman conditions, which tell us when a generic graph is rigid. And this is a very beautiful theorem, but for special types of grids, we know that we can have a better characterization of rigidity by using graph theory. So when we're considering grid-like frameworks, so here we have 2 grid-line frameworks, and we know that if we place diagonal bars in these frameworks that follow special rules or that have a special configuration, then the framework will be rigid. And this is a theorem by Volker and Crapo. And there are also other people that have considered grid-like structures, but the theorem is basically pretty much the same. So let me recall it. Whenever you have a grid like this and you want to make it rigid, we can put some diagonals in the faces of the squares. And here, instead of using diagonals, I'm going to use plates just to keep the parallel with the initial quasicrystal structure that we considered. So the theorem says that to make the framework rigid, what we do is we create a graph where our nodes are the columns and the rows of our framework. And whenever we put a plate on a face, we put an edge on our graph. And this framework is going to be rigid whenever the graph on the right is spanning and connected. Okay? And this is the theorem of Volker and Crapo that says that a bracing of an n cross m grid is rigid if and only if the corresponding graph, bracing graph is spanning and connected. And again, this theorem works even if your grid doesn't look like a grid of squares, okay? So you could have parallelograms of different sizes, like the one I have here on the right, okay? Good, so we are interested in studying the rigidity of a Penrose framework, and what we see is that we can also do a similar argument as the one that Volker and Crapo did for grids. Okay, so what we do is the following, is that in a Penrose framework, a maximal succession of contiguous rhombi whose common edges are parallel is called a ribbon. So what you see on this picture is a ribbon, and the edges that are parallel in this ribbon are the ones that are highlighted. And rigidity for a Penrose framework is very similar as for a grid. And we associate some graphs to a Penrose framework. So we associate to it a ribbons graph and a bracing subgraph. So in this graph, the vertices are going to be the ribbons of the Penrose framework. And you have an edge between 2 ribbons whenever the 2 ribbons intersect. Okay. So here we have a Penrose framework. We have drawn all the ribbons on this framework. That's the graph that you see on the right. And then the colored subgraph is the graph that corresponds to the faces that have plates on them. Okay, so again, either a plate or a diagonal brace. Okay, and the theorem, it's very similar as the one that we had for grids. And it says a braced Penrose framework is rigid if and only if its bracing subgraph is spanning and connected. And now, to the best of my knowledge, these first appear in the work of engineer Ture Wester. So he has a paper where he proposed this theorem. And what we did in our group in the Illinois Geometry Lab was to revisit this theorem and try to write a more rigorous proof of the theorem. And what we noticed is that the theorem is a little bit more general than just for Penrose framework. So one of the important properties that Penrose frameworks have in common with grids of squares, for example, is that all of the bars have the same length. But as you saw for the previous case, you can have grid-like structures where you don't care too much about the lengths of the bars so long as they are still parallelograms when they deform. So what we notice is that we can generalize Wester's theorem a little bit more to say that a simply connected framework made by parallelograms is rigid if and only if its bracing subgraph is spanning and connected. Okay, so let me clarify this point. So Wester is telling us this kind of framework is rigid if you follow the graph argument. So here, what you're seeing, it's a picture of an actual physical model of a Penrose framework where we plated this structure, and it actually holds rigid if you just hold it from the top. And here, all the you have two types of rhombi, skinny and fat, and this framework is rigid. And now, in the slightly more general version of the theorem, what we're saying is that you can start drawing any kind of framework. Let's say we start with the square here at the left, and then so long as you only draw parallelograms in different directions, like the one you see here, you will still have a theorem of rigidity based on graph theory. Okay, you can draw the ribbons of this framework and decide, how to put faces in this framework to make it rigid. Are there any questions so far? I feel that I'm going a little bit fast.
So I have a question. What exactly is the definition of a Penrose framework?
Oh yeah, sorry. It's just you take a piece of a Penrose tiling.
Or what's
Like
the definition of Penrose tiling?
I'm sorry?
Or what's the definition of a Penrose tiling?
Oh, a Penrose tiling is a tiling of the plane by a fat and skinny rhombi in such a way that this tiling does not have any translational or rotational symmetry.
Gotcha. Thanks.
So that's like an aperiodic tiling, and that's the connection to quasicrystal. So in 3D, a quasicrystal is something that is tiling the 3D space by two rhombohedra, but it doesn't have symmetries.
Gotcha. Thank you.
Okay. Oh, can you go over how you get the ribbons again? Sure, yes. So you start at a rhombi, let's say the bottom blue rhombi, and then you look at the parallel edges of the contiguous rhombi, okay? And you do this for all of the possible edge directions on your framework, okay? So if you look at the framework that you have in this slide, for example, we have 7 ribbons, and you can start by, any point on any edge that is like on the boundary, and then just continue along that ribbon. Then you're done, you switch to another edge, and so on. And this notion of ribbon is well defined so long as you are talking about parallelograms in the framework. Okay, so that's how we get like a slightly more general statement than for Penrose frameworks. Okay. Okay, so this is what we could understand from what happens in 2D and what happens, you know, with Penrose frameworks, and also with, let's say, more general frameworks.
Eliana,
Made of,
you had another.
oh, there's another question. When we talk about minimal condition, should the graph be just a tree or a minimal tree? What's the difference between just a tree or a minimal tree? But I think minimal conditions, let's say, is just a tree. You mean tree of the smallest size, or okay, I guess I'm not understanding the question, but if you want minimality, yes, just brace a tree. And I guess if you want even more minimality, try that tree to be smaller. I'm not sure. Okay, are there other questions? Okay. Okay, so that's what we did for 2D, but we're interested in what happens in 3D. Wait, I think, okay. We're interested in what happens in 3D, so let's start from the same starting point that we started for the 2D case, which is, you know, is there anything that we can say for grids of cubes that we can say for 3D quasicrystals? And there has been, you know, a lot of work in, of course, rigidity for 3D frameworks. There are several, so here I have a list of different papers that I found in the literature, which tell you how to, they have different versions of rigidity for 3D grids of cubes. And, you know, these are nice results, but I think they are not considering the problem the way that we wanted to approach it for the artistic application. And in many of these papers, you see that the results are concerned with how do you brace a grid-like framework with diagonals, like the one you see on the left. So you take a face of the grid and you put a diagonal on that. Or you take two opposite vertices of the cube and you put a diagonal on that. Or even some of these papers consider, what if you put a diagonal, you know, across several squares? To the best of my knowledge, there is no theorem that tells us how do we minimally brace a grid-like framework with plates. So the picture that I have on the right here would be, you know, a plating of the cube that makes it rigid. And we are interested in that case. We're interested in bracing the framework with these plates. And my goal is to you know, try to see if we can generalize the 2D rectangular framework to the 3D cubical grid, and hope that we can do that for 3D quasicrystal frameworks as well. So let's, the attempt that we have to, that we did to try to do this was to formulate the following. So we define this concept of stratum. So a stratum for us is the generalization of the concept of ribbon. Okay. So for the ribbon, what we did is we chose a direction and we looked at the contiguous rhombi in that direction for which that edge was parallel. Think of the stratum in the same way. So you pick an edge of one of the cubes and you look at all of the edges that are parallel to that edge in all of the possible directions, parallel to that edge. So that gives us a stratum. Okay. And we can fix a stratum, okay? And anytime you fix a stratum, your framework gets chopped into two pieces, basically. And you can deform along that stratum. So here's what we call a shear along a stratum. It's clear from the picture, I hope. And then we want to consider, when we were thinking about 2 dimensions, we had that 2 ribbons met at a rhombi, right? And what we have for strata is that 2 strata meet at a tunnel. They are also called tubes in the literature, but let's call it tunnel. So we have that any 2 strata meet at a tunnel. And now the question that I have for you all rigidity experts is, could I possibly have the following conjecture question? I'll formulate it as a conjecture. A 3D grid can be made rigid under shears along the strata by plating at least one face in each tunnel. That's the conjecture that we have, but we don't know if it's true or not. We do believe it, and we think that this will help us understand the rigidity of 3D quasicrystal frameworks. And let me just show you some computational or empirical evidence of our conjecture. So what you see here is a interactive computer animation. So what you see right now is that this framework is deforming by doing shears along strata. Okay, so it's cycling along the different strata of this framework, and you see that when you cycle along these shears, this framework deforms. Okay? And now what we can do is we can plate some faces in this framework, and again cycle through these deformations that are shears along the strata. And you see that, well, when you have some frozen faces, then, well, the deformations of the framework are different, right? And what we have here is that in this function, we have plated one face in each of the tunnels. And when we again try to cycle along all the shears of the strata, what we see is that the framework rotates as as one piece. So we see that the framework is rigid, and we think this conjecture of plating the tunnels holds, but so far we haven't written a proof of it. We have some computational evidence, and we could not find anything similar in the literature. So that's where we are at the moment, and that's all I wanted to say. Thank you.
All right. Thank you, Eliana. I guess I will open it up for questions. Okay, so I have a question about the conjecture, and maybe like some approaches you've tried. So is there like some I guess variety whose, yeah, I guess algebraic matroid here, or like so some variety that's like supported on maybe the faces in your like 3D framework, whose
Um,
algebraic matroid like, or whose spanning sets in the algebraic matroid gives you the rigid like ways to like plate them. Is there a way to look at it like that?
um, I have not looked at it like that. I have tried to I would like a statement that is similar to the 2D statement,
Mhm.
where you have a graph. So like, if it's spanning and connected, then it's rigid. But this is a little bit more subtle. So I think we would have to first, define that ground set in which we would define the matroid, and then go to like the direction that you're suggesting. But no, I haven't looked at that.
I mean, it's like, what if you take like the ground set to be like, yeah, I don't know, each of your faces or something, and like you map each face to like its area. Um,
Sorry, could you repeat that? I missed it.
like if you take like the ground set, for example, to be each like square face, like okay, say you're doing like a rectangular, like each rectangular face is a element of the ground set, and then you have like the map from your like particular framework to like the area of each face or something, and then I don't know. This is just a random idea. Maybe it's not worth too
Um,
much, but
it could be like, there are, when you have the grid, there are different like geometrical things that you could have in mind. Like, you can have the strata, you can have the ribbons. There's also some other things that they define that are called strips, or like, different geometrical units that you want to like uh, put together to make something that makes sense. Um, but yeah, that could be one possibility. I see there's a question in the chat. When you say rigidity, do you mean infinitesimal rigidity? No, I mean, uh, I mean, just, you're, when actually, when I mean rigidity, I mean, these the distances between two vertices are not supposed to change, I guess. And yes, and what the conjecture says is that we're sort of only restricting to these shears along the strata. But perhaps it's true if you even consider more general motions. Is there any known result on rigidity? Not that I know of. I was wondering if perhaps in the oh, okay. Okay, okay, I see there's another. Okay, let me just finish the answer for the previous question. Is there a known result on rigidity? So not that I know of. I think perhaps maybe I'm not looking at the correct literature, and we're talking about like panel and hinge frameworks for which there might be a result. So I don't know. Let's go to the question of Sean. I think I have misunderstood, but a single cube isn't a single cube. No, so for me, maybe I did. So maybe in the definition of strata, the cube, so you see here, we have three strata on this cube, which are the three different directions. So in this case, so you could think of the conjecture as sort of like as a shadow. Okay, so if you look at the cube from the top, it has a shadow that is plated. If you look at the cube from the side, it has a shadow and is plated, and so on. So the cube wouldn't be a counterexample, I think. So Jessica is asking if did I translate this problem into a graph theory problem as in the 2D case, and the answer is no, but that's what I would like to do. Yeah. Does aperiodicity play a role in your 2D theorem? No, it doesn't. Yeah. It was surprising. I mean, when we were studying this rigidity of a Penrose framework, like the one you see here, we thought, oh, maybe there's something special about these aperiodic tiling or the rhombi that make this framework. But the nice thing is that really you could be very creative, and as long as you follow the rule that you add just like parallelograms at each, say, joint, and you do it in such a way that you don't create any weird holes in your framework, the notion of ribbon is well defined, and you can decide rigidity of the framework based on that graph criterion.
Eliana, you have a raised hand. I'm just gonna unmute.
Sure.
George, you can go ahead and ask your question.
No, I just wanted to make a comment, Daniel. The area issue is interesting in the case of the quasicrystals. The 3D quasicrystals, the area is related to the shape of the rhombi. So yes, actually volume in this case. There are only two volumes. But if you leave but we clearly don't need the strict definition of the Penrose quasicrystals to formulate the theorem in 2D and probably not in 3D. Another item, someone else asked, are there any examples? We almost had a proof in the following restricted case that the shapes, say a cube, never leaves parallelity. In other words, that the edges remain parallel to each other. Now, this is an artificial condition. The only thing that we were able to come up with was if you play with what I think in German is called Meccano, and otherwise it's called something else. If you make the framework with an additional rigidity built at the joints, how the edges fit together. But that's kind of artificial. That's more of a toy answer. I think there's no particular mathematics in that. That's just two comments I wanted to make in relation. The other thing is that no, there doesn't seem to be anything as simple as a graph, because the strata intersect not in a yes or no way, they intersect in a tube. So there's an intermediate. So we're not talking about graphs anymore. We're now talking about simplicial complexes, and there aren't any really good theories for that. That's just what I wanted. That's some of the difficulties that we haven't solved.
Thank
Okay.
you, Duarte. Are there results about which cubes need to be braced in a 3D framework of parallelepipeds to get a rigid framework? I think the answer to that is no, if you are thinking about the general framework. However, there's a special type of framework they consider in the literature, which is they call it a T-story building. So you think that your framework is sort of grounded on like a floor where the rods of the first floor are attached. And in that case, they reduce the rigidity of the grid to the two-dimensional case, and they tell you how to brace the diagonal faces. So there are some, the short answer is there are some results that deal with special cases, but to my knowledge, for the general case, just a cubical framework like in space, I don't know. I don't think so. What can be said in the 2D case for frameworks that are not simply connected, maybe with a certain genus? Yeah, I've seen, I don't recall the results, but I've seen papers that consider grids when you have a window or like a hole in the framework. But I think there are some people studying those, but I don't know what are the results. But yeah, some people study those.
Right, any other questions? All right, well, I guess if not, thanks everybody for coming, and thank you, Eliana, for speaking. And the video and slides will be posted for this soon.
Okay, great. Thank you everybody for your questions, and see you next time.